So in this video, I'm going to recap normal distributions. So normal distributions are really common type of distribution. A lot of things that you would just normally measure in nature are going to follow this normal distribution. So as an example, if you got a whole bunch of people together and you measured their heights, what we would expect is those heights would follow a normal distribution. So let's use that as an example. So what we're going to put on the x-axis here is those heights that we would have measured of the people. And often we call this variable that we're measuring x. On the y-axis here, what we would be measuring is the relative frequency. So how often each of those different heights are observed. So relative frequency. And what you tend to find is that what's going to happen, it's going to look something like this. Okay, so this is why normal distributions are sometimes known as bell curves, because this kind of looks like a bell. So what we can see is that we've kind of got this big cluster here where most of the people's heights are actually sitting. And then there's only a few people that end up with really small heights and a few people with really big heights. Okay, so there's a few different things that we can kind of mark onto this graph. So one of them is the mean, or the average result. And that's going to happen for a normal distribution at the center, okay, because it's like all nice and symmetric. So we use mu as the symbol to represent the mean. And the other thing that we need to describe this data is kind of how spread out it is. So if the data is really spread, maybe like, let me draw it a bit better, maybe like this. All right, it's going to have one standard deviation that you would measure. Alternatively, if you had something like this for your distribution, it's all about the same mean, but this time there's not much variation away from that mean value, so therefore you would have a small standard deviation. Okay, so sigma is the symbol that we use to represent standard deviation. And this is describing to you the spread of the data. So is it really spread out like this green line, or is it really concentrated like this grey line? The bigger the standard deviation, the more spread it actually is. So the data in this kind of form, where we've got our x, or heights is the example I'm using, plotted against the relative frequency, it's not particularly useful for calculating probabilities. So say I want the probability that people sit within this kind of zone, okay, say the mean is 150 centimeters. What if I want to work out the probability of being between 130 and 160 or something like that? All right, so if you wanted to do that based on this direct data, it would perform a lot of integration and other mathsy stuff, which is a lot of effort and not really worth it. So the way that we get around it is we normalize this graph, okay, in terms of x, to some other graph in terms of a variable z, okay, and this z value is going to be, the normalized value. So every z value is kind of the same no matter what type of data you're looking at. So what happens when we convert to this other type of data? Is rather than being plotted in terms of your variable, we're going to plot it in terms of this new one called z. And let's take this blue one that we were playing with before. It's going to kind of look the same, except what's going to change is where the mean sits. So previously this mean was the mean of the height data. So say, what did I say before? 150 centimeters as an example. So when you convert it in terms of z, what's going to happen is that the mean value of your new data set is always going to sit at 0. Okay. The other thing that's going to happen is you're going to change your standard deviation. So previously this standard deviation, if it was for the heights, it would have been like, say, 20 centimeters or something as your standard deviation. But when you convert it to this other type of data, this z data, your standard deviation is automatically going to go to 1. Okay, so these are the same, all right? This is just in terms of x. This one's just in terms of z. All that we've done is normalized it so that we're always going to have a mean of 0 when we're dealing with this z data, and we're always going to have a standard deviation of 1 when we're dealing with this z data. So how do you convert between the two? It's quite a simple formula. So the formula is that z is equal to x minus mu on the standard deviation. So Z, that's the value that's going to get plotted on this one. X is whatever value you're interested in from your height data, which was measured in terms of X. Mu, that's going to be the mean that you had up here. And the standard deviation is going to be whatever one you had up here as well in terms of your X data. So with this formula, you can convert anything from this graph onto the other graph down below. Now really all this is measuring is how many standard deviations, I'm just going to use this, are you away from the mean. Okay, so it's just measuring relative to the mean, how far away are you, and it's taking into account this standard deviation, so how spread the data was to begin with. Okay, that's all this formula is doing to normalize it into this nice mean of 0 and standard deviation of 1 format. A couple of nice things now that we're in this other format, it's really easy to calculate probabilities. So all you need to do to calculate the probability of something happening is to calculate the area under the curve for what you're interested in. So if there's a specific band that you're interested in, so between, I don't know, here and here, you would just mark that off and calculate the area under the curve for that. And there's a series of tables which are able to assist you with that process. And there's also Excel and other kind of tools that can help you with that as well. I'm going to go through using those various different tools in the example videos, not in this recap one. The other cool thing though, for working out these probabilities is that the total area under the entire curve is equal to 1. So let me just rub this out now. So area under entire curve is equal to 1. Alright, so the last thing I want to point out is that if you divide this in half, the area under the curve of half of it, if the whole thing is 1, this half is going to have an area of 0.5. Same thing for the other side. Alright, if it's half of the area of the total thing, it's going to have an area of 0.5 as well. This can become useful when you're using the tables in order to solve for various different probabilities. Just keep that in mind. Alright, so that's pretty much it in terms of this recap video, and I'll see you in some of the examples.